So binary numbers and its operations, that's what we're going to see. Why binary? As I mentioned, it's very simple, tedious, but simple. So these are the example of binary numbers. We have seen one example. So these are the other examples. As you can see, there is only 1 or 0. There is no other numbers, only 2 possibilities for a particular position. So this pretty much we have seen the conversion. So in our daily life, we use 10 base numerals, and we have converted 10 base numerals in the base format. And then we have seen a 2-based numeral as well. So this is pretty much showing exactly same thing which we saw in the whiteboard. So 6 into 10 raised to 0, 7 into 10 raised to 1, 10 raised to 2, and 10 raised to 3. So that is how that number. Similarly, a 2-based or a binary number. So both are the same. 2-based numerals and binary number, they're exactly same thing. It's just 2 different terminology. I may use both in the series. We have a 1, and then there was another 1. Here is a 0, and in the end there is a 1. Again, same principle. We have seen this. We have. So that's the way the calculation is done. Some terminologies around 2-based numerals. So bit. You might have heard about bit, right? When you talk about internet connection speed, bits per second. A lot of common places, bit comes into the picture. So bit is nothing but one binary digit. Yes.
Why Bitcoin is called so? It has in relation with bit.
Why Bitcoin is okay. So little out of the context question. So Bitcoin is named, the bit in front means that it's a digital currency. So the currency is actually in the form of bit, this binary numbers we are studying. I don't want to go into the details of it, but that's why it's getting that name.
Yeah. So there's some relation with this bit.
Exactly, very true. This is exactly the bit in the Bitcoin. Yes, that's related. Yeah. So bit is nothing but a number of a binary number, 1 digit of a binary number. Okay, pretty simple. So a bit can be either 1 or 0, no other possibilities. This is again pretty similar to the 10-based numeral. So a 3-digit 10-based numeral, how many numbers it can represent? So 3-digit. Let's get back to the drawing board. So a 3-based numeral, so 3 digits. So I'm going to draw squares for 3 digits. What is the amount of numbers? How many numbers can this 3-digit represent? So the maximum is 999, right? And it starts from 0. So total 1000. So 1000 different numbers it can represent. A 3-digit decimal number, the normal number we use. This is also equal to 10 raised to 3. Correct, right? 10 to the power 3.
Question.
Yes.
How did it become 1000 numbers? If we jumble up the numbers, it can be more than 1000, right?
Is it? Let's take a small example. Good question. So probably the viewers may have the same question as well. So I don't think I did the right thing by taking a big number. So this is a good point. So let's take the small example. So let's take the example of a 1-digit number. Okay. So there is only one box here. Okay. So how many numbers it can represent?
10.
10, exactly. So starts from 0 to 9. Yeah. So that is 10. All right. Now let's take the example of 2-digit. So where it starts, again, starts from 0 and ends in 99. Okay, so 99 is the highest, and this is the starting point. So tell me a combination between this and this, which is not in the list of 0 to 100. Does it make any sense? Yeah. So how many numbers between 0, 0 and 99. So how many numbers?
100.
100. And it is equal to 10 raised to
2.
2. That's correct. Now let's come back to this example. All right. So we have proved that a 1-digit number has 10 raised to 1. Okay. And a 2-digit number has 10 to the power 2 maximum numbers, and a 3-digit number. What is the smallest number possible? Again, 0. Yeah, this is the smallest number possible.
Sorry about that. I didn't think much when I asked that question.
That's okay. That's absolutely fine. Yeah. So the total number of possibilities is 1000, which is 10 raised to 3. Okay. Now let's see if you can predict in the case of 2 base numerals. Okay. So there is a 2-based numeral which is of 3-bit. Normally we don't say 3-digit, it's a 3-bit, but I may say 3-digit for the sake of explanation. So this is a 3-bit 2-based numeral. Can you predict, without any calculation, can you predict how many different numbers it can hold? 2 to the power 3. That's it. That's correct. So let's do the exact same methodology to come into this number. So 1, if it is 1 bit, there is a possibility that it could be either 0 or it could be 1. Yeah, it could be either 0 or 1. So that is 2 raised to 1. So 2 possibilities are there, 2 different numbers you can represent. So 2 raised to 1 equal to 2. So 1 digit. So this box is 1. So this is also 1. Now let's take a 2-bit number. Okay. So this is a little more difficult. So I'm going to write it here. 0, 0, 0, 1. Yeah. 1, 0 and 1, 1. Very good. Excellent. So those are the different possibilities of a 2-bit number. 2-bit number.
Binary.
Yeah, binary number. So how many different numbers are here? 4. Correct. Which is equal to 2 raised to 2. That's correct. So expanding it to n-bit. So an n-bit. So this is n. So an n-bit 2-based numeral can have
2 raised to n.
2 raised to n digits. Correct. This is a very important, even in programming. If you are doing advanced programming, this calculation does matter to you in networking, storage, everywhere. All right. So let's get back to the slides. Yeah. So we have seen this. How did we arrive at this particular value? We have seen that, and we also discussed this one as well. Yeah. So let's get back to the next slide. Yeah. This is the binary numbers to decimal conversion. So you have a binary number, say 1011. We need to convert this to a decimal number. We have seen the operations. 1 into 2 raised to 0 plus 1 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3. So we have seen this in the first demo. We have seen that. So this is how the calculation goes, this conversion, pretty straightforward. Any questions on this calculation? All right, cool. So here is another operation we're gonna learn to convert from decimal to binary. So we have a decimal number, say for example 3, and we need to convert it to binary digit. Okay. So that's what we're gonna do. Let's get back to the whiteboard. So we are back to the whiteboard. What we're gonna do is we're gonna convert a decimal number to binary. So let's take the example of number 3. Okay, so what we're going to do is we're going to convert this 3 to a binary number. So first operation I'm going to perform is divide 3 with number 2, and I'm going to take the remainder of that operation. So I'm not going to take the decimal point which is coming. So it is 1.5 when you divide 3 with 2. So 3 is here, 2. The actual value we're going to get is 1.5. I'm not going to take the 0.5. Instead of taking the 0.5, what I'm going to do is I'm going to give 1 as a remainder. The quotient is 1 and a remainder is 1 as well. Okay. Now again I'm repeating the process. 2 dividing with 2. Remainder is 1 and quotient in this case is 0. Now we got 2 remainders and I'm going to put this value here. And I'm going to put this value here. Okay, 1 and 1. So I'm going to ignore the other values, especially the quotient. I'm not going to use it. Just the remainders matters in this conversion operation. So let's check the answer. So 2 into 2 raised to 1 into 1 plus 2 raised to 0 into 1, which is 3. So the answer is correct. Now, any questions?
No.
All right. So let's take another example. This time, let's take the example of 6. Now we're going to convert 6 into binary. So what is the first operation we're going to do?
Divide by 2.
Divide by 2. That's correct. What is the quotient?
3.
3. What is the remainder?
0.
0. That's correct. And what's the remainder here?
1.
1. And quotient?
1.
1. That's correct. So 2, 2 again. This 1 is not equal to 0. So we need to continue the process.
1.
1. And this is going to be
0.
0. Okay. We got 3 remainders. This one is going to go here. And this one is going to go here. And this one is going to go here. So 1, 1, 0. Okay. So let's check the answer. So 2 raised to 2 into 1 plus 2 raised to 1 into 1 plus 2 raised to 0 into 0. So this is equal to 4 plus 2 plus 0 equal to 6. So the answer is correct. All right. So before we move on, let's do one more small number to get that practice. So this time you are going to tell me everything. So the number is 9. So we're going to convert it to binary. So 9, what is the first operation?
Divided by 2.
Yeah, divide by 2. What is the remainder?
1.
1. Now, what is the quotient?
4.
4. That's correct. Divided by 2 again. We are repeating the process. What is the
0.
no remainder?
2.
2.
1.
1.
0.
This is not 0. So 2.
1.
1.
0.
0. Yeah. So we got a 0. We are stopping the process. We got 3 remainders.
4.
Yeah, 4 remainders. That's correct. Yeah, 4. So this one will go here. This one will go here. This one will go here. And this one will go here. All right. So
Question.
1, 0, 0, 1. Yes.
Can we take this remainders interchangingly? You have to take in the same order, or?
You have to take in the same order. Yes, that's right. Yeah, you have to take in the same order. So pretty much what we are doing is that we are reversing the process of multiplying. So let's check the answer. So 2 raised to 3 into 1 plus This 1 is here. 2 raised to 2 into 0 plus 2 raised to
1 into 0.
1 into 0 plus 2 raised to 0 into 1. Yeah. So this is going to be 1. This is going to be 0. This is going to be 0. And this is going to be 8. So 8 plus 1 equal to 9. So pretty much what you're doing right here is reversing this. Yeah. So pretty much it is reversing that operation. So the answer to the question is yes, you have to take this remainders in this order, this exact same order. If you mess up the order, you get different number. As a matter of fact, this is not a very important operation for our purpose. The upcoming operations are very simple and they are more important for our purpose. So this is just, we are getting some familiarity with the 2 base numerals and getting a hand of it. All right, so now let's get back to the slides.